The Earth is in the grip of many unseen forces. The gravitational pull of sun and moon exert an influence on the sea. Winds driven by solar energy churn up the atmosphere and make our weather. The magnetic field of the Earth gives shape to the aurora that brightens the night sky with its eerie glow. But today, instruments make the unseen reveal itself. With their help, scientists everywhere observe, measure, and explore the invisible forces that shape planet Earth. To this day, man sailing the oceans relies on an invisible force to guide him: magnetism. Magnetism is a means of generating power. Turbines with magnetic fields convert water power into electricity. Giant magnets are used by nuclear scientists to control the motion of atomic particles in high-energy accelerators. Man has long been familiar with magnetism. The Greeks first encountered it in a district called Magnesia, from which our word magnet is derived. Here, more than 2,000 years ago, rocks were found that seemed to possess a magic power. They attracted iron. Superstition became linked to magnetic rock, or lodestone as it was called in later times. People believed that it could attract fish. Lodestones were supposed to put demons to flight. Sailors thought that a ship held together by iron nails was doomed when it sailed past a lodestone mountain. Then man began to study magnetism scientifically. He learned that every magnet has two opposite poles, and that like poles repel, unlike poles attract. William Gilbert, physician to Queen Elizabeth, published the first extensive study of magnetism in the year 1600. Gilbert tried to explain why the compass points northward. He suggested that the Earth's interior is composed of lodestone, and that the Earth itself acts as a giant magnet. He believed that a field of magnetic influence surrounds our planet, and that this field moves the compass needle. Today we know that all magnets are surrounded by magnetic fields. The fields are invisible, but a demonstration with a bar magnet and iron filings can make them reveal their form. The filings line up along curved paths called lines of force. A field much like this, as if a bar magnet were buried in its core, surrounds the Earth. Theoretically, this field extends to infinity, but its strength decreases rapidly with the distance from Earth. The source of the magnetic field is not magnetic rock, as Gilbert suggested. Today we believe that the interior of our planet is far too hot to retain permanent magnetism. The Danish scientist Ørsted was among those who explored the true source of magnetism, when early in the 19th century he studied another natural force, electricity. Ørsted found that magnetism and electricity are related. This can be seen when a compass needle is deflected by an electric current. Then, in 1823, the Frenchman Ampère discovered that when he sent electric current through a coil of wire, he produced a magnetic field like that of a bar magnet. This showed that electricity is a source of magnetism. The English scientist Michael Faraday in turn demonstrated that magnetism can produce electricity. He built a generator called a dynamo, in which he rotated a metal disc through the magnetic field of a horseshoe magnet. This generated an electric current. When the magnet is replaced by a coil of wire carrying electricity, the coil, through its magnetic field, generates the same electric current. Today, scientists think that the Earth's magnetic field is produced by a dynamo-like mechanism deep in the interior. Currents flow in the hot core. These currents, together with the rotation of the Earth, act somewhat like Faraday's dynamo and create the Earth's magnetic field. Throughout the world, the study of geomagnetism is carried out in specialized observatories. These observatories are built without iron or steel, so that magnetic measurements will not be affected. Before approaching the highly sensitive instruments, scientists must leave behind all magnetic objects. With the help of these instruments, geophysicists try to answer many questions. Is the field uniform, or does it differ from place to place? Does it change with time? And if it does, why? The key to these problems lies in precision measurements of the magnetic field, measurements of its intensity and direction. The horizontal direction of the field can be demonstrated with a compass needle. The needle does not generally point to the geographic or magnetic poles, as many people believe. Instead, it is given its direction by the magnetic field, which is irregular. For instance, in Los Angeles, the needle points 15 degrees east of true north, whereas in New York, it points 11 degrees west. We measure the horizontal direction of the field by determining the difference between the direction of the needle and true north. The vertical direction of the field can also be demonstrated with a magnetic needle. The closer the needle moves to the magnetic pole, the more it dips. The angle of dip indicates the vertical direction of the field. The basic instrument for the scientific study of the magnetic field is the magnetometer. It measures the field's intensity and direction with great accuracy. Essentially, it is a very sensitive compass in which a small bar magnet is suspended on a gold fiber. By observing the direction of the magnet, which acts like a compass needle, the scientist measures the horizontal direction of the field. Intensity, or the force exerted by the field on a magnet, can be measured by observing how fast the magnet oscillates when moved out of its position of rest. The world over, scientists measure the intensity and direction of the field. This team in the Philippines is making a reading with a portable magnetometer. Since the magnetic field is not a static force and changes in strength not only from place to place, but from decade to decade, readings must be repeated regularly. Today, the geophysicist can make detailed and specialized surveys in almost any location. These new techniques are especially useful in mapping permanent local distortions in the magnetic field. Such distortions are caused by variations in the composition of the Earth, for example, by deposits of iron ore. But measurements on land can cover only 1/4 of the globe. The field must also be mapped over the oceans. An airborne laboratory has been designed specifically for geomagnetic surveys. Its heart is an electronic magnetometer mounted in gimbals to compensate for the motion of the plane. Readings like this are also made on ships, but the plane, with its greater speed and range, now makes it possible to map in a few hours an area that previously would have taken weeks. Observations made around the world are sent to mapping centers where they are collated. The observations are transferred to punch cards and analyzed by electronic computers. The final products are comprehensive maps of the magnetic field. To keep track of the changing field, the maps are revised periodically. This map shows the intensity or strength of the field. Measurements over the past 100 years reveal that during this period, the field has grown weaker by about 6%. Other maps show the direction of the field. Scientists plot all locations where the compass points in the same direction and connect them with a line. The dynamic nature of the field is demonstrated by this sequence of maps covering a period of 50 years. These variations reflect changes deep in the Earth, in the dynamo mechanism that produces the magnetic field. The study of these changes helps man to understand more about the core of planet Earth. Rock formations provide us with important clues to the ancient history of the magnetic field. Cores are taken from rock formed millions and hundreds of millions of years ago. The present direction of the field is measured and marked. In the laboratory, the rock cores are prepared for examination. It is thought that millions of years ago, when these rocks were formed by the cooling of molten materials, the mineral crystals in them became magnetized in the direction of the magnetic field of that time. By comparing the ancient magnetic direction of the minerals with the magnetic field of today, some evidence shows that over millions of years, the field has undergone a substantial shift. To explain this shift, provocative theories have been evolved about the past of our planet, suggesting, for instance, that the crust of the Earth has moved. Such a move would cause an apparent wandering of the magnetic pole, which scientists have plotted from rocks of different ages. This plot of the pole, based on analyses of European rock samples, shows it shifting from a position near the equator to its present location. However, when American rock samples were used, a different plot resulted. A possible way of reconciling these plots is to shift the American continent toward Europe until the tracks of the magnetic pole form an almost identical path. This supports the intriguing but still unproved theory that millions of years ago, the European and North American continents may have been much closer together. Although the magnetic field is closely linked to events on Earth, it is also profoundly influenced by events far out in space. Electrical events in space produce fluctuations in the magnetic field of the Earth. A magnetic measurement made at a certain time and place may differ from a measurement made there a few hours earlier or later. After years of observation and analysis, scientists have concluded that most of these fluctuations are related to... During the International Geophysical Year, the study of magnetic fluctuations and their relationship to the Sun was carried to remote regions of the Earth. For the first time, scientists of many nations made extensive magnetic readings on the vast continent of Antarctica. Russian teams, which established a station at the South Geomagnetic Pole, also set up equipment near the coast to record fluctuations automatically for months at a time. While recordings are made by portable equipment all over the world, more than 100 permanent observatories contribute systematic readings of magnetic fluctuations, made continuously over years and decades. The most commonly used instrument for measuring fluctuations or short-term variations in the magnetic field is the variometer. It employs a small magnet and a mirror suspended on a fiber. Light is focused on the mirror. As the magnetic field fluctuates, the magnet, and with it the mirror, oscillate. The light is reflected by the mirror and directed at a recording instrument. Here the motion of the magnet is traced on photosensitive paper. This record is called a magnetogram. Magnetograms have revealed several types of magnetic fluctuations. One of these fluctuations, plotted on this chart, is predictable and occurs regularly every day. It is caused by the Sun. The Sun illuminates most intensely that region of the rotating Earth where the Sun is directly overhead. The Sun's heat and gravitational pull result in electric currents in the upper atmosphere. These currents produce the regular daily variation in the Earth's magnetic field. The Sun, moreover, is a direct source of irregular and unpredictable magnetic disturbances. Our nearest star is a violent and explosive concentration of hot gases. From time to time, explosions occur in the Sun's atmosphere and eject into space invisible streams of charged particles. Charged particles in motion constitute an electric current. Scientists believe that a day or two after the explosion on the Sun, the current approaches the Earth, where it interacts with the magnetic field. Through processes we do not as yet understand, this interaction in turn produces gigantic electric currents, some 60 miles above the Earth. These currents cause violent magnetic disturbances on Earth, which we call magnetic storms. The storms are often accompanied by spectacular auroral displays in the night sky, here shown in time-lapse photography. They are associated also with blackouts in long-distance radio communications. Today, new techniques provide direct information about magnetic storms. Sounding rockets have detected and measured the electric currents that are thought to produce the storms. Every 11 years or so, events on the Sun increase the frequency and intensity of magnetic storms. Solar disturbances are linked to turbulent areas on the Sun called sunspots. Scientists know that the number of sunspots increases and decreases in a cycle lasting about 11 years. They have discovered also that magnetic storm activity increases and decreases in a parallel cycle. Because the sun revolves on its axis in 27 days, solar disturbances may remain active long enough to make their presence felt on Earth a second time, 27 days later. While events on the sun affect the magnetic field of the Earth, the magnetic field, in turn, exerts a controlling influence over some electrical events in space. Early in the 1900s, Carl Størmer, a Norwegian mathematician, calculated the influence of the magnetic field on charged particles in space. His conclusions and those of his teacher, Dr. Birkeland, are the more remarkable, since man had not as yet penetrated space, and their work had to be entirely theoretical. Størmer did not know of cosmic rays, the invisible high-energy particles shooting through space in large numbers and at speeds approaching that of light. Yet Størmer provided the basis for our present understanding of the relationship between the magnetic field and the motion of these charged particles. At the equator, cosmic rays approach perpendicularly to the lines of force, and most of them are deflected. Only the fastest and most energetic penetrate. But at the magnetic poles, many of the particles approach parallel to the lines of force and undergo no deflection. Even the weakest can penetrate to the Earth's atmosphere. Thus, the magnetic field selects and rejects cosmic rays, the highest energy particles known to man. Størmer's calculations suggested also that some low-energy particles would not only be deflected, but could actually be trapped by the magnetic field. To examine this theory, laboratory experiments were devised. In the Størmertron, named after the Norwegian scientist, a glass chamber is filled with gases to approximate conditions in the atmosphere. A model of the Earth is placed inside the chamber. It contains a magnet which produces a magnetic field like that of the Earth. When a stream of charged particles with low energy is directed at the sphere, it is first deflected by the field, then trapped by the lines of force. The particles surround the Earth with a shell. This experiment supported Størmer's calculations in the laboratory. But today, scientists can extend their observations into space itself. Data reported back from satellites and space probes led to a dramatic discovery. The Earth is surrounded by great zones of charged particles, mainly from the sun, which are trapped in the magnetic field. These are the Van Allen belts, extending some 50,000 miles into space. Their discovery by American scientists confirmed the brilliant theoretical speculations of Carl Størmer. To study the trapping of charged particles by the magnetic field under controlled conditions, a bold and complex experiment was devised. Ships carried high-altitude rockets to the South Atlantic. Small atomic bursts, some 300 miles above the Earth, would release into the atmosphere a known quantity of charged particles. Special scientific stations were set up. They were to observe the movement of the particles to determine the influence exerted on them by the magnetic field. At other stations, sounding rockets with special instruments were prepared for launching. On shipboard, shortly before firing, last-minute checks on weather and atmospheric conditions were carried out. Then the experiment began. The atomic bursts released charged particles into the atmosphere. Størmer's predictions, made 50 years ago, were confirmed when the particles were trapped by the lines of force and moved in spirals along them. They filled a crescent and traveled back and forth within it. Immediately after the detonation, auroral displays were observed at two locations, clearly determined by the lines of force. Under the influence of the magnetic field, the particles slowly drifted eastward around the Earth, forming in about an hour a great shell. This was, in fact, a man-made Van Allen belt. Sounding rockets penetrated and measured the shell. Some time later, a satellite in orbit could still detect a residue of the particles, demonstrating the remarkable stability of the magnetic field in space. Scientists throughout the world continue to explore the Earth's magnetic field. Measuring and mapping it, they use their findings to probe deep into the core of our planet and far out into its atmosphere. But man is pushing beyond the Earth's magnetic field to explore the magnetic fields of the Moon, other planets, and interplanetary space. For magnetism, the invisible force that moves the compass needle on planet Earth, can give man a better understanding of the far reaches of the universe.